The second part of Unit 6 is focusing on gases and the properties of gases and the mathematical relationships between all of the gas properties, therefore what we call the gas laws. So first, before we get into the gas laws, we need to focus on the variable properties of gases. So there's really 4 variables that can change when you're describing a gas. It's volume, pressure, temperature, and the amount of gas or the moles of gas that are in the container. Now, when we are doing gas law calculations, there's a couple of really important things that you should do, and it's focusing on the units. So when you're talking about the volume of a gas, or really it's the volume of the container that the gas is in, mathematically we need to have that unit in liters. So make sure you have your volume in liters. If it's not, do a conversion to get there. You need to have your pressure in ATMs. You need to have your temperature in kelvins, and you need to have it in moles. So if it's not in moles and you know what the gas is, you need to make sure that you convert your grams to moles to be able to do the mathematical calculation. So make sure that you focus on those units of those variables when you're starting to do some gas law calculations. Talk about temperature. So in gas law calculations, we have to use temperature in the scale of Kelvin. This allows us to have a direct relationship between volume and temperature. The reason here is Kelvin is a scale that there is no negative number on. And the reason is, if you are talking about the changes in volume and temperature, and if your temperature goes from a positive value to a negative value, well then, because volume and temperature have a direct relationship, your volume could get potentially negative based on the math. And you can't have negative volume because that would be less than 0, and you can't have less than 0 volume. So you have to make sure that you are focusing on this unit. So when you are doing temperature calculations, you need your temperature to be in Kelvin. And how do you convert that? Well, here's your equation. Kelvin is equal to degrees Celsius plus 273. It's technically 273.15, but we just round it to 273. So let's say that we had a gas that was at 25 degrees Celsius. So if we are at 25 degrees Celsius, to get that to Kelvin, we just add 273, and that gives us 298 Kelvin. And that's the number that we can use for our gas law calculation. So always convert your temperatures to Kelvin. Now pressure. Pressure is something that is measured, and it describes the force per surface area. So it's the force that the gas is exerting on the area of the container. So the units for pressure are really important. We measure pressure in different units depending on what component that you're using to measure the pressure. For example, this drawing over on the right hand side is a manometer, and a manometer will measure pressure in units called millimeters mercury. And basically when there's no pressure on the liquid that's in the U-shaped tube, the manometer, you can see that the levels are equal on both sides. And so that's just filling up the tube. But when we exert a pressure on this, that's going to cause this side to go down, and in turn this one's going to go up, and the difference or the displacement between those two sides would be the pressure that the gas is exerting on it. So when you're looking at pressures, there's different tools that we use to measure pressure. We use a barometer, we use a manometer, and the unit is dependent on the tool that you use. So when you're measuring pressure, It could be in units of atmospheres, or torr, or millimeters mercury, or kilopascals, depending on the tool that you have. So we're going to have to be able to convert between all of those units. So make sure you're comfortable with these numbers, and make sure you're comfortable with doing those conversions. Of conversions before we move on. So if our unit is 826 torr, and we want that to be in millimeters mercury, well, we're just going to have to do the conversion for that. So we know the relationships. So we know 1 ATM is equal to 760 millimeters mercury, which is equal to 760 torr, which is equal to 101.325 kilopascals. So if we are trying to convert from torr to millimeters mercury, we can just use the relationship between torr and millimeters mercury. So we can say 826 torr is equal to, or let's do a dimensional analysis, for every 760 torr, that is 760 millimeters mercury. And my units cancel out, and that's going to leave me with 826 millimeters mercury. What if we wanted to go to kilopascals? Same idea, 826 torr. Then the relationship is 760 torr is equal to 101.325 kilopascals. And that's going to give me a relationship. Torrs cancel out. And we grab our calculator and we find 110 kilopascals. Same idea, let's go ahead and go to ATM, 826 torr, and 760 torr is equal to 1 ATM. And therefore, grab our calculator, 1.09 ATM. So you got to be able to convert between your pressure units. Make sure that you're comfortable with that. It's really, really important that you understand those pressure units. The first law that we're going to talk about is called Dalton's Law of Partial Pressures. And it says the total pressure of a gas mixture is equal to the sum of the partial pressures of each of the gases in the mixture. So if we have a container that has air in it, so here's our container with air in it, and air consists of oxygen and nitrogen and argon and water vapor and carbon dioxide. All of those things are in this container of air. If we want to know what is the pressure of the air in the container, well, it's equal to the sum of the partial pressures. So the partial pressure of the oxygen plus the partial pressure of the nitrogen plus the partial pressure of the argon plus the partial pressure of the water vapor and all of that, add them all together, and that gives you the total pressure in the system. So Dalton's Law of Partial Pressure says the total pressure in the system is equal to the sum of the partial pressures. We're going to use this when we want to find the total pressure in a container after a reaction happens, or if we can measure the total pressure in the container, we want to know what's the partial pressure of the gases. So here's a couple of examples. We are going to talk about a container, and in the container there's nitrogen, oxygen, water vapor, and helium, and these are all the partial pressures, and so we want to calculate the total pressure of the system. So first, notice that all of these are in different pressure units. And if they are all in different pressure units, we need to make them all become the same units. So we have to convert them all to the same unit. Because two of them are in ATM, I'm going to go ahead and convert the other two to ATM. But the question may ask you, well, what's the pressure in a certain unit? So you have to convert to that unit. But let's go ahead and do the conversions. So the 1.26 ATM of nitrogen, that one's fine because it's in ATMs. The millimeters mercury of oxygen, we need to convert that. So we're going to go ahead and mathematically convert that, knowing the relationship is 760 millimeters mercury is 1 ATM. And so when we calculate that, we get 0.747 ATM. And the kilopascals of water, we got to convert that to ATMs, and we know there's 101.325 kilopascals in 1 ATM, so we'll convert that, and that gives us 0.952 ATM. And now we have all the partial pressures of all of these things, and they are in the same units. So now all we have to do is add the pressures up to get the total pressure. So the total pressure would equal the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the water vapor plus the pressure of the helium. And so now you're literally just going to plug everything in and add them up. So 1.25 plus 0.747 plus 0.952 plus 0.678, and add all of that up, and you get a total of 3.64 ATM. So, given the partial pressures, we can calculate the total pressure. Example that we're going to do, same idea, but this time we're going to attack it from a little bit different way. So it says we have a 2.52 liter. So now let's get into some of our gas laws. The first law that we're going to talk about is called Boyles Law. And Boyle was a scientist who was investigating the relationship between pressure and volume. Now you have to remember that the particles of the gas are constantly moving, and they're bouncing off the walls of the container. So in this diagram we have this container with the top of it is a movable piston. So we can push down on this part, and that will cause the container to collapse, and the piston will push down, and that's going to change the volume. So here in the first one, the piston is almost all the way open, and in the second one, all we did was push down the piston, and that reduced the volume of the container. The third one, we pushed it down even more, and that reduced the volume of the container. Now, notice that the gas particles are much closer together, and because they're much closer together, they're going to push harder on the walls of the container, and that's going to cause the pressure to change. So Boyle looked at the mathematical relationship between these things, and he discovered that they have what's called an inverse relationship, meaning if the pressure goes up, then the volume went down, or vice versa. If the pressure goes down, the volume goes up, or like we saw in our drawing, what happened here in the second one, the pressure was increasing. And why is the pressure increasing? Well, because the volume decreased. So we end up with this mathematical relationship, and here's Boyle's law. He mathematically said, if you multiply the pressure and the volume at a certain condition, if you change one of those variables, well, then the other one is going to change in an inverse relationship. And you can mathematically calculate the new pressure or volume given the new pressure or volume. So let's look at an example of that. So in this example, we have a gas that's in a 2.5 liter container, and the pressure is 3.65. So I'm going to go ahead and write that down. So the initial pressure is 3.65 ATM, and the original volume was 2.5 liters. So now that we have that, we're going to change the situation. So what's the new situation? It says, if the volume of the container changes to 1.7, predict what will happen to the pressure. All right, so what did the volume do? The new volume is 1.7 liters, which means the volume decreased. And if the volume decreased, what is going to happen to the pressure? Well, because they have an inverse relationship, that's going to cause the pressure to increase. Now let's use Boyles' law to figure out how much did it go up. So remember, Boyles' law is P1 V1 is equal to P2, V2. And now what are some of the things that we know? Well, we know P1 and V1. And we know V2, so then that's going to allow us to calculate P2. So I like to plug in things into my equation and then rearrange. It doesn't matter which way you do it. So I'm going to say P1 was 3.6 ATM. And V1 is 2.5 liters. And I'm going to go ahead and move my new volume over here. So I'm going to say 1.7 liters is going to equal to P2. So now I just plug all of that into my calculator and I find P2 is equal to 5.4 ATM, which shows us that indeed the pressure did go up, just like we predicted. So let's do it again. This time we're going to change the situation a little bit. So again, we're starting with a volume of 2.5 liters and a pressure is equal to 3.65 ATM. And now we're going to change the pressure. So the pressure now is going to be 652 torr. And the question is, what's the new volume? Now we have one little problem here. Our little problem is that our pressure unit is not in the right unit. So we need to change that. So how are we going to change it? We know the relationship. 760 torr is equal to 1 ATM. And that's going to give me 0.858 ATM as my pressure. Now we're just going to plug it into Boyles' law. So we're going to say P1 V1 is equal to P2 V2. P1 is 3.65 ATM. V2 is equal to 3.5 liters. And we're going to divide that by our pressure, 0.858 ATM. Notice that these units go away and I'm left with liters, which is good because that's what we're trying to find. What is our new V2? And so V2 is equal to 10.6 liters. The next law we're going to talk about is called Charles's Law. Charles was a hot air balloonist, and he liked to study with what he was interested in, hot air balloons. And here's what he found when he was looking at this. If we held the pressure and the amount of gas constant in a situation, if we change the temperature, then the volume also changed. And he found that when we change the temperature, however we change the temperature, the same thing happened to the volume, meaning it was directly related. So as one goes up, the other one goes up. As one goes down, the other one goes down. And here is the equation for Charles's Law. So it says that V1 divided by T1 is equal to V2 over T2. So when you look at those things and you do the calculations. If we know 3 of the 4 variables, we can calculate the 4th. So it's just showing the mathematical relationship. If volume doubles, well then the temperature had to double, or vice versa. So let's look at a Charles Law calculation. A hot air balloon has a volume of 36.4 liters at a temperature of 30 degrees Celsius. What will happen to the volume if the temperature is raised to 42 degrees Celsius? So let's start with what we know. So the initial volume is equal to 36.4 liters. And the initial temperature is equal to 30 degrees Celsius. And what is the new situation? Well, the question is, what is the volume if the temperature is raised to 42 degrees Celsius? Now, here's one of those situations we've got to watch out because our temperature is not in Kelvin. So we want to go ahead and change our temperature to Kelvin. So we just need to add 273. So if we add 273 to this, we get 315. If we add 273 to this, we get 303. And that gives us our new temperatures in Kelvin. And now we can just plug it into the equation. So V1, which is 36.4 liters, divided by T1. And I'm just going to algebraically move this one over. So I'm going to bring my T2, 315 Kelvin. And that's going to give me my V2. Notice that my Kelvin units go away, leaving me with liters. And so now I just plug it in my calculator. V2 is equal to 37.8 liters. And in actuality, here's what happened. The temperature went up. And look, so did the volume. Volume went up. The next gas law that we're going to discuss is called Gay-Lussac's, and Gay-Lussac's is the mathematical relationship between pressure and volume. And notice each time we come up with these new laws, some other things are being held constant. For example, in this law, we are holding volume and the amount of gas is being held constant. So we are making sure that those two things aren't changing because they might have a relationship on an effect on these relationships. So in this one, we're talking about pressure versus temperature. And again, here's the gas law. P1 over T1 equals P2 over T2. And we're back to a directly related situation. P1 and T1, if pressure goes up, then so does temperature, because they have a direct mathematical relationship. Remember that your temperature must be in Kelvin. So here's the big one, the combined gas law. Basically, the combined gas law is just combining the 3 laws that we just talked about. So it combined Boyles Law, Charles's Law, and Gay-Lussac's Law all into one big combined gas law. And it relates how changing the pressure and the volume or the temperature can affect all things in these variables. So we have our combined gas law, which is P1 times V1. Oh, look, that looks like Boyles right there. And then if you look again, divided by T1, V1 over T1, well, look what that is. All right, there's Charles, okay? And then if you look at the last relationship, you'll find there is Gay-Lussac's. And in each of those situations, these things are staying constant. So, For example, in Boyles Law, pressure and volume are changing, temperature is staying constant. So when you look at these things, you'll see that they are showing up in the combined gas law. So really you don't have to remember Boyles versus Charles versus Gay-Lussac's. As long as you remember the combined gas law, you know all three here in one fell swoop. Now I wrote down here, because algebra tends to be an issue in this, this is another form of the combined gas law where we got things out of the denominators. So P1 times V1 times T2 is equal to P2 V2 T2. All we did was move this over here, move this over here, and that helps you with your algebra, especially when you're calculating new temperatures, because students tend to mess up when they're calculating a T2. So here's a little practice with the combined gas law. So we're going to take a balloon, and we know three things about the balloon. We know the volume of the balloon, we know the pressure of the balloon, we know the temperature of the balloon. And then we're going to change something. In this case, we release the balloon up into the atmosphere, and it rises until the pressure inside the balloon is lowered, and the temperature is also lowered. So changing those two variables is going to have some mathematical effect on the new volume of the balloon. So we need to find these things we want to find what is the new volume of the balloon. So let's start with what we know. First, we got to check our units. Now notice that our temperatures are not in Kelvin, which means we're going to have to change them and make them into Kelvin. So let's go ahead and change those. So 22 degrees Celsius plus 273 gives us a new temperature of 295. And 4 degrees Celsius and add 273 gives us a new temperature of 277. And remember that these are kelvins. All right, now let's set up our problem. So to start off with, what is our initial pressure? It's 1.75 ATMs. And then our initial volume is 3.5 liters. And our initial temperature is 295 Kelvin. And that's going to equal the new situation. So the new pressure is 0.653 ATM times the new volume, which we don't know, divided by the new temperature, which is 277 Kelvin. And now we just have to do some algebra. We're going to move this over here by multiplying. We're going to move this over here by dividing. And we end up with 1.75 ATM times 3.5 liters times 277 Kelvin divided by 295 Kelvin times 0.653 ATMs, and that is equal to what V2 is. Now, if you set this up correctly, your units should cancel out. We have ATMs on the top, ATMs on the bottom, kelvins on the top, kelvins on the bottom, and we are left with a unit of liters, which makes sense since we are trying to calculate a volume. And now we just type all of that into our calculator, and we find that the new V2 is equal to 8.81 liters. Always watch your sig figs. There's your calculation for the combined gas law. So if you have a basic idea of these gas laws, you have an understanding of the mathematical relationships between pressures and volumes and temperatures, and you understand the combined gas law, you'll be able to easily do all of these kinds of gas law questions. They're all what happens when the situation changes kind of questions.